One other use we can get out of the disk method volume formula is it gives a way to explain this volume of a sphere formula. When I go through in a class about volumes in the non-calculus class, I have a good way to explain, well, the volume of a box is length times width times height, volume of a cylinder is pi r squared h. I can kind of explain that. But when I get to the volume of a sphere formula, I guess there's ways, but it's provable, I guess you might say, when we get to the disk method here. Because a sphere, what a sphere is it's a circle or semicircle, right? Sphere, to generate a sphere, one way we could construct a sphere is to take a semicircle and rotate that about the x-axis. Would that generate a sphere? So it's rotating a semicircle about the x-axis, which brings up then the way we do that is with this disk method. Now, a couple of things. In disk method, we need volume is integral a to b pi times f of x squared dx. So the only deal is here, well, one of the deals is I got to figure out my function. I know it's a semicircle, and then I've got to let's talk about, first of all, the other issue is the limits here. All right, so these I'm doing with respect to x, right? Because I want to do my integration with respect to x, and so I need these x values. I would want to go from this x to this x. Well, since it's a semicircle, I'm talking about a radius r semicircle, so this would be r. What would this be? Minus r, right? So my limits, and there's a couple other ways we could do it probably, but one way is I could say, let's go from x is negative r to positive r. Good with that? Okay. Now the other thing, let's figure out our function here that I square. Well, I know the equation of a circle in the center is 0, 0. A circle is x squared, center is 0, 0, radius r, is x squared plus y squared equals r squared. And so this semicircle here, the top half of the circle, well, what I need is, it's a y equals equation. So to get the semicircle, I'm just going to solve this for y. So it'd be y squared equals, and then subtract the x squared, both sides. Square root both sides. To get the y equals by itself. And that's, the top half is the positive. If I wanted the bottom half, it'd be minus the square root of r squared minus. But that's my function right there. Y equals the square root of r squared minus x squared. So in the formula, that's what I square. I square the square root thing. Okay? All right, so to prove this, so that's going to be my volume. Let's see if it works out like we think it will here. All right, so here's how this works. Well, the good thing is I'm squaring a square root, and so that square root and that square are going to cancel out. So this just becomes r squared minus x squared. So that at least one good thing happens here. The square root and the square cancel one another out. All right, now here's the next little thing. All right, so I need to do the antiderivative, right? So it's going to be, volume is going to be pi times, all right, now, antiderivative of that. R is our number here for the radius. R is just a number. It's a constant. This is just a number. So the antiderivative, if you have a number, the antiderivative of that if it was 5, the antiderivative is 5x. Well, this is a number like that, so the antiderivative would be r squared x. And then, of course, the antiderivative of that is 1/3 r x cubed. Yeah, this is just a number. So when you antiderivative, you just add an x to it. Okay? And then I'm going to go from negative r to r. All right, so if I plug those in, these are x values, so I plug those in for x. So that becomes r squared times r minus 1/3 r cubed. And then I plug the minus r, I have r squared times minus r minus 1/3 times minus r cubed. So that looks like a bunch of terms, but the good news is they're all going to be like terms. That'll be r cubed, this will be minus 1/3 r cubed. Notice that would be minus r cubed, and that would be minus r cubed times minus 1/3 would be plus 1/3 r cubed. With me? But hey, look at that. Yeah, these are all like terms, if you will. They're all r cubed terms. So that gives me volume equals pi times, well, let's go ahead and just write it. That would be plus r cubed, and that would be minus 1/3 r cubed. Look at that. Basically what I've got here is 2r cubed minus 2/3 r cubed. But I can do even better than that. I just combine the r cubes and the minus 1/3. But I can even do better than that because those are again r cubes. If I do 2 minus 2/3, 2 is 6/3 minus 2/3, that'd be 4/3. Pi r cubed, 4/3 r cubed. Aha! Isn't that what the volume of a sphere formula is? 4/3 pi r cubed. So anyway, it takes a little bit of work there, but can prove that. The other thing I was going to mention before we get to our other method today is okay, so our say we take y equals f of x rotated about the x-axis, a to b. The volume is integral a to b, we'll just say pi times f of x squared dx. Well, what if our rotation is about the x-axis? Well, so if I take, so yeah, that's taking this y equals f of x from a to b, rotated about the x-axis. And that'll give me that volume if I do that. Well, what if I take some function and like that, and it's going from C to D here. So I want to take that and rotate it about the y-axis. Well, I think it's obvious there. I want to do my disk or my integration with typical rectangles that way. And so that's, to get the volume of that, that's going to be the integral from C to D. And I'm going to integrate with respect to y. And so my formula is going to change. Instead of a function of x, right, it needs to be a function of y, because I'm integrating with respect to y. So it's going to be pi times f of y squared dy. It's the same formula, you're just doing it in terms of y to get that volume. So that's volume with x equal f of y rotated about the y-axis. And I'll do one of those in just a second, but let me point out while I've got both of these up here. All right. So this one I'm integrating in respect to x. So the typical rectangle is this. This one's I'm integrating in respect to y, so the typical rectangle is that. I pointed this out last time, but once again, notice here, both of these are the disk method. So this is disk method too, but it's rotated about the y-axis. But in both cases of the disk method, notice how the typical rectangle and the axis of rotation are related. We talked about this last time, but the typical rectangle here is vertical. The axis of rotation is, the x-axis is horizontal, but they're perpendicular. The typical rectangle and the axis of rotation are perpendicular. But notice it's the same way here. It's disk method, and notice that the typical rectangle is perpendicular to the axis of rotation. So in both cases of that disk method, and in the washer method too, disk method, washer method, the typical rectangle is perpendicular to the axis of rotation. Why do I mention that? Because a couple of problems in one of the homework sections, you have to decide whether to use disk method, washer method, or some other method we'll talk about in a moment. And then this is how you decide. If the typical rectangle and the axis of rotation are perpendicular, that's disk method or washer method, which that's go between two functions. Washer method, remember, that's if you're going between two functions. But the typical rectangle and axis of rotation are perpendicular, then use the disk method. So if it doesn't tell you which method to use, this is how you decide to use disk method. All right. All right, so let's find the volume of the solid. Generated by rotating the region between y equals 1 over x to the fourth, x equals 0, y equals 1, and y equals 4, about the y-axis. So we want to find that volume. 1 over x to the fourth. I think I know what it looks like. I'll make sure. Let's see, 1 over x to the fourth. Yeah, so it comes in something like that, and the other side too. But so I want to do region between that, x equals 0, which that's the x-axis. I'm sorry, x equals 0 is the y-axis. Y equals 1 to y equals 4. So I'm going to rotate that about the x-axis, rotate that about the y-axis. So it's symmetrical. And so that's the little region I'm going to rotate. The region enclosed by that, I mean, we could go to the other side, but don't need to do that. That's why we want to rotate. Region between those. So yeah, this hopefully is obvious that I want to do my typical rectangles horizontal, which I didn't say which method, but let's examine it. All right, so I'd want to integrate here with respect to y. First thing I could establish is I want the typical rectangle. I wouldn't want to go up and down because I'd be going between this curve and this curve for part of it and this curve and that curve for another part of it. So I don't want to do that if I don't have to. If I just integrate with respect to y, then I'm going from the y-axis out to that curve. So integrate with respect to y, first thing. And you probably guessed because where we're at in our lecture here, but just point out again, it's still going to be the disk method because here's the axis of rotation, here's the typical rectangle, they're perpendicular, that's disk method. So I want to do the disk method, the one though with integrate with respect to y, well, that's one we just talked about, is pi times f of y squared. And then we go from C to D. So I want to do that. Now, a couple of issues here. Good news is, I've got my C to D because those are the y values I'd go between, so it's 1 to 4, isn't it? I didn't put the labels on there, but it's y equals 1 to y equals 4. The issue here we have is I need this function of y, which is an x equals equation, right? That's what I need. On these. Well, the problem is I've got a y equals equation instead of an x equals equation, so I've got to adjust that. How would I do that? Well, y equals 1 over x to the 4th. I just solve it for x. Instead of y equals, I need x equals. Sometimes we have to do that. So we've got to adjust that, that equation a little bit. Yeah, I'd multiply both sides by x to the 4th. One way to think of it to get that. So it'll be x to the 4th y equals 1. And then all you have to do, well, the next step then to do would be trying to solve for x. So divide off the y. And so that would be x to the 4th equals 1 over y. And then x, so 4th root all that. 4th root of 1 over y. And let's go ahead and write that. Which means, think of it a couple of ways. 4th root of 1 over 4th root of y. 4th root of 1 is still 1. And then 4th root of y in the denominator, wouldn't that be y to the negative 1/4 power? So that basically is the way I would want to write my, my function in terms of function y. Y to the negative 1/4. That's what this is, the function of y. Then I'm going to square that. Okay? Is that good? Question? Well, how would I do that? It's not too bad. Just have to figure out, well, what's negative y to the negative 1/4 squared? Well, power to the power you multiply. So negative 1/4 times 2 is 2/1, those cancel, so that's negative 1/2. When you multiply those, you get y to the negative 1/2. So then I do my antiderivative, so it'll be pi. Antiderivative, add 1, so the new y power would be 1/2 power. Do the reciprocal thing in front, so it'll be 2/1, y to the 1/2. Evaluate that from 1 to 4. So that'd be pi times 2, 4 to the 1/2, minus 2 times 1 to the 1/2. Well, that's pi times 4 to the 1/2, that's square root of 4, which is 2. 2 times 2 is 4. 1 to the 1/2 is still 1. 2 times 1 is 2. Oh, it's 2 pi. Question? So that little, yeah, if you think about what that would look like if you rotate it all, it's kind of looks kind of like a lampshade, kind of a narrow looking lampshade. That's what I can, I guess it'll be around there. Excuse my drawing skills, but it's kind of what you, I thought of the lampshade, solid lampshade. Anyway, question? We good?